We should finish this module up by talking about a few important properties of conductors, specifically conductors in electrostatic equilibrium. Now, I warn you, this lesson will be an exercise in how well you can follow along with logic, so it'll be pretty technical without a lot of equations. As always, feel free to rewind or slow down the video if you need to. We talked about conductors before and how they allow charge to flow freely through them. Inside conductors in electrostatic equilibrium, however, all the charges in the conductor have stopped moving. In other words, the charges have no reason to move. That's what it means when we say electrostatic equilibrium. Equilibrium means the charges aren't moving. Another way of representing the fact that the charges have no reason to move around is to say that the electric field is zero inside of the conductor. The reason why is, imagine if the electric field weren't zero inside of the conductor. Then any free electrons inside the conductor at these points would feel a net force and they would start accelerating. But that contradicts the fact that the conductor is in equilibrium. The conductor can't be in electrostatic equilibrium if free electrons are busy accelerating around. Free electrons accelerate if they feel a net force due to an electric field. Therefore, there must be no electric field inside a conductor in electrostatic equilibrium. And that takes care of our first principle. We've carried out a logical argument to show us that the electric field is zero inside a conductor in electrostatic equilibrium. But what else can we say about this conductor? Now, what if we use Gauss's law inside this conductor? We're told the electric field everywhere inside the conductor is zero, so that means the flux through this surface we've just created is also zero. There's no field going through the surface, so that would mean the charge enclosed inside the surface is zero. This works for any surface we choose so long as we stay inside the conductor. If we're anywhere outside though, all bets are off. The flux through the surface here is non-zero, completely consistent with the fact that the net charge inside the surface is also non-zero. We see these two units of negative charge inside. What this means then is that the net charge on any conductor has to be situated at the surface of that conductor, like we see here. There can't be any net charge inside the conductor here, since you could then imagine a Gaussian surface that surrounds this net charge and creates an electric field somewhere on the inside. But that would violate our first principle, which says that there's no electric field inside a conductor in electrostatic equilibrium. And now that forms for us our second principle. The last one describes the behavior of the electric field at the surface of the conductor. At the surface, the electric field isn't zero, but the electric field has to be perpendicular to the surface if the conductor is in equilibrium. The reason why is suppose it weren't perpendicular. In other words, suppose the electric field at the surface had a perpendicular component and a parallel component. Then the parallel components would cause charges at the surface to move along the surface. But if the conductor is in electrostatic equilibrium, no charges should be moving at all in the first place. Once again, we've ran into a contradiction. We can't have conductors here in electrostatic equilibrium if the electric field at the surface has any parallel component, because that would allow charges to move along the surface, which would violate the fact that there shouldn't be any charges moving at all in a conductor in electrostatic equilibrium. That then concludes our three properties of a conductor in electrostatic equilibrium. These properties don't seem obviously useful on the surface, but we'll go over some problems in which they turn out to be quite useful.